Hello, and welcome to Matthias's Rust Corner. In this video, we will cover polymorphism and how we can use it to manage asynchronous closures in Rust. Higher rank trait-bound concepts will be explored, and we'll touch on pin unpin and why futures must be pinned. And if you wait all the way to the end, I'll tell you why the new async fn traits aren't helpful in this scenario. Before we get started, I have made the GitHub repository associated with this video series. It contains examples and exercises relevant to these videos. Please check it out if you want to play along. Let's get started. Let's first explore when you will want a collection of asynchronous closures. One scenario for this is if you're making a message dispatcher. This is a software component that ingests one or more messages and forwards it to 0 or more receivers based on some criteria. Forwarding or processing a message is most likely an asynchronous operation, so being able to use asynchronous closures is necessary. A UI system may want to use async closures for callbacks and event handlers. A web server could use asynchronous closures to process requests. The list of use cases is pretty much endless, so we'll stop here. Let's stick with the dispatcher example throughout this video. In order to create a container to hold several callback closures, we're forced to use dynamic dispatch. If your container will only hold one closure, you can use generics, but as soon as you have more than one callback registered, this is no longer possible. This is because each callback we create has a new unique type, even though their call signature is the same. If you want to know more about how closures are implemented in Rust, go watch my video on function pointers and closures. However, for our dispatcher, where we wish to hold several different closures in our container, we need to use what we call a trait object. In Rust, we use trait objects to dynamically dispatch to implementations of traits for an unknown type. We can use either a smart pointer of din trait or ref din trait. In both cases, the only things accessible to us are the data pointer and the vtable pointer for the hidden concrete type. We call such a pointer a fat pointer since it's actually consisting of two pointers. The vtable contains the call address of each trait method implementation for the hidden type. When the compiler inserts a call to a trait object method, it will first read the address of the method implementation from the vtable, and then make the call to that address. The data part of the trait object fat pointer is passed as the receiver of this call. Since the only thing we know about our trait objects is that they implement a certain trait, and where in memory its data lies, we can accept pointers to several different hidden concrete types. More formally, we call this idea polymorphism. It means that an unknown set of concrete types are hidden behind a common, well-known interface. Now that we know what the din closure is, let's look at the async part of this problem. For all intents and purposes, an async closure in this context is a closure that returns something that implements a future. You'll quickly realize that futures returned by an async block suffer from the same issues as a closure. They are anonymous and generated implicitly. This means we have to make our closures return a dynamic future as well. Let's see what happens when we set the return type to box din future. The compiler complains that the future does not implement unpin. Now, the topic of pin unpin is probably a video on its own, but very briefly, self-referential structs cannot freely move in memory, since they're containing a pointer into their own memory. So if an instance of a self-referential struct was moved, its member field that contained the pointer into its own memory location would be invalidated. To solve this problem, Rust introduced the unpin autotrait, which is implemented for all standard types and all types containing exclusively unpin types. A type that is unpin is guaranteed to have no constraints on moving it in memory. Self-referential structs must use the phantom pin marker to make themselves not unpin. Then there is the pin struct, which is used to wrap a pointer type. It's effectively a guarantee that, even if this pin type is not unpin, its value will never be moved while pinned, so it is safe to access it in a context where it otherwise may have moved. Think of it as pinning a post-it note to a pegboard. As long as it is pinned, it will remain in the same location on the board even if you leave the room and come back. Unless you have a very naughty, i.e. unsafe, cat in the house. The main reason for pin-unpin's existence is to avoid problems with self-referential futures. These can easily occur when writing async functions or blocks like the ones we see on the screen now. The future created by the useName function is both a member of and holds a reference to data inside the future made by the self-referring future function. If these could move in memory after they were pinned, polling them would cause unsoundness. To ensure that pol doesn't access invalid self-referential addresses, the pol method requires the receiver future to be pinned. This is a fairly complex topic, and I've included further reading materials in the comments below. In our application, this means we need to return a pin pointer to a future. The most common approach to this is to express the return type as a pin box din future. As you can see, the compiler is now happy with us polling the future. Let's put our new knowledge to use and build a message dispatcher which will simply forward messages asynchronously to a number of receivers. Each receiver will also return a number back to the dispatcher. Let's pretend it represents the number of processed bytes. We'll use a vec to hold our callbacks. The dispatch method will simply forward the messages as a string to all the callbacks. And here we create the futures unordered set from the futures crate and put all the dispatch futures into it. When we iterate through the set, we print the output of each dispatch as they resolve. So far so good. We can now take our async closures and put them in a container for further dispatch. But what if we wish to pass values to our closures by reference? As seen here, we run into some rather uncomfortable error messages when attempting to make a closure taking a str reference parameter. It's complaining that our str parameter doesn't outlive the lifetime of our future. This is because when Rust attempts to elide lifetimes for trait objects, it uses something called the default trait object lifetime bound. I've posted a link to the documentation page for this feature if you wish to understand it further. In our case, where our fn trait has no lifetime parameter, this resolves to static by default. Since our future captures the str reference, which doesn't outlive tick static, we are not allowed to return this future. But fret not! By giving our trait object an anonymous lifetime constraint, we can apply the normal lifetime elision rules. This means the compiler now binds our closure to the lifetime of our input str, and everything is great. This works for one reference. But what if we add the second str argument? As you can see, the anonymous lifetime trick no longer works, since there's more than one input lifetime to consider. We can use higher ranked trait bounds to solve this. We will not dive into higher ranked trait bounds in this video, since it's yet another big topic by itself. The TLDR is, we use the for tick A syntax to annotate the relationship between our input references and the produced future. The lifetime tick A in this case is not a specific lifetime. It represents a lifetime that will be resolved by the compiler so that all the input references are valid for it. If this is a bit tricky to think about, don't worry. Just accept that with a for tick A syntax, we can annotate all our input references and the output future with tick A and go about our merry way. It's worth mentioning that since our future no longer has a static lifetime, we cannot spawn it as a separate Tokyo task, for instance. This is because Tokyo's spawn method requires futures to be both sent and static, since tasks may live for the entirety of the application and be sent between worker threads. You may be wondering, what about the newly stabilized async event traits? The short answer is, they aren't DIN compatible. This means we have no way of dynamically dispatching to them, since the return future must be a sized associated type of the closure. Finally, you can also use dynamic references instead of boxed closures. The advantage of this is that you can keep your closures on the stack, offering performance benefits in certain applications. Here, you see how this works. It's very similar to the boxed version. The drawback is that your dispatcher needs to connect its lifetime to the closures. As you can see here, when we try to return the dispatcher which holds the reference to our on-stack closure, the compiler tells us this is illegal. This is because the dispatcher will outlive the function stack's lifetime, invalidating the closure reference. The benefits are that allocating the closure may be a bit faster, and in some scenarios you will have fewer cache misses when calling them. Let's sum it up. Today, we explored how to use polymorphic async closures with trait objects in Rust. We learned how we can store them both on the stack and on the heap, and how to deal with the futures they produce. And we learned how to deal with common lifetime problems with these usage patterns. That's it for today. Please let me know in the comments if you want a video on pin unpin or higher rank trait bounds next. Don't forget to subscribe to get notified about subsequent Rust videos. Goodbye!